Hey everyone, we are from Group 10 and we are going to explain about heat capacity. Hi, my name is Noor Hidayatul Jannah BT Mod Hayadeen. I would present about history. In the 18th century, the Scots sea scientist Black noticed that equivalent masses of different substance needed different amounts of heat to raise them through the same temperature interval, and from this observation he founded the concept of specific heat. Then in 1780, based on data supplied by Richard Kirwan and João Magellan, gave a clearly stated definition of heat capacity, together with the first table of specific heat values. In the early 19th century, the French physicists Pierre-Louis Gélong and Alexis-Thérèse Petit defined specific heat as the heat required to raise the temperature of a small quantity of substance by a fraction of 1 degree. The Pierre-Louis Gélong and Alexis-Thérèse Petit also created the Gélong-Petit law. Its statement that the gram atomic heat capacity, which is the product of the specific heat capacity and the atomic mass of an element, remains constant. This law was then modified to apply to metallic element only, now is used to calculate the approximation at intermediately high temperature. The definition of heat capacity is the amount of heat energy required to raise the temperature of a given quantity of matter by 1 degree Celsius. For this given matter, their heat capacity depends on its size or quantity. The unit are J, K or J per degree Celsius. For the specific heat capacity is defined as the quantity of heat, J, absorbed per unit mass, kilogram, of the material when its temperature increases 1 K, or 1 degree Celsius. Its units are J, kilogram K, or J, kilogram degree C.
Hello, my name is Janani Vijayakumaran. So for my part, I want to explain the equations and theories involved in the problems regarding heat capacity and specific heat capacity. So basically, as we all know, heat capacity and specific heat capacity is a path dependent. So to find heat capacity, the formula is energy required divided by change in temperature, and to find heat energy, the formula is mass multiplied by the specific heat capacity of any change in temperature. When we integrate the formula, we get Q equal to the integration of C respective to dt. Then, next slide is about specific heat capacity at constant volume, CV. So the formula is CV equals to du divide by dt respective to constant volume. When we rearrange the formula above, we will get du equals to CV respective to dt. So through the integration, we will get change in internal energy as equals to integration of CV respective to dt from temperature 1 to temperature 2. So in mechanically reversible, Q equals to number of moles multiply with change in internal energy is also equals to number of moles multiply with integration of CV respective to dt from temperature 1 to temperature 2. The next slide is about specific heat capacity at constant pressure, Cp. Thus, the formula is Cp is equals to dH divide by dt respective to constant pressure. In closed system, we use change in enthalpy equals to integration of Cp respective to dt from temperature 1 to temperature 2. In mechanically reversible, Q is equals to number of moles multiply with changes in enthalpy and is also equals to number of moles multiply with integration of Cp respective to dt from temperature 1 to temperature 2.
So here is the applications related to CV and CP. In first diagram, the container contains 1 mole of gas where the volume remain constant with unknown temperature. In the second diagram, the container contains same 1 mole of gases where it has 2 layers with different unknown volume, V1 and V2. The difference between 2 volume is known as dV where the pressure is constant. The second example, it's about land breeze. Basically, land breeze is a cyclic process where the low pressure rises up and high pressure will go down. In cold surface, it has low specific heat capacity where the temperature decreases. The next slide is about the specific heat capacity for ideal gas. The change of enthalpy and internal energy are dependent of temperature change. Cp and Cv are changing with temperature where the difference is equals to R, which is gas constant. The formula is Cp equals to dH divide dt is also equals to du divide by dt add with gas constant, R, where it is also equals to Cv add with gas constant, R. Next, the temperature dependent equation is Cp equals to dH divide by dt with constant pressure, and it is also equals to dH divide by dt, which is meant by Cp respective to temperature. This is an example question for heat capacity. Calculate the heat capacity for methane in the range of temperature from 533.15 Kelvin to 873.15 Kelvin increased by 10 Kelvin. The solution of this question using MATLAB is in the next slides.